So we are honored to have him back with us tonight at his home museum of OMSI. This is our 18th season. We are going to do space this year. So, and this year Intel is still our sponsor. So can we get a big thank you to Intel? You're very intelligent. And can we get a thank you for OMSI for letting us be here today? And Dr. Barratt? All right. And I'm going to stop talking because I think there's an amazing presentation coming. So, Dr. Michael Barratt.
Okay, thanks very much. Fired up crowd, that's great. I'm psyched to be here, and I want to talk to you guys a little bit about what's on the screen here. But when we're done, we're going to have some time for questions and answers. If you don't have questions, I'm going to start asking you questions. So really think about what you want to know about space. Don't leave here without knowing something. If you have any questions, you can embarrass me. I have 5 kids. So, you know, if you don't know how to go to the bathroom in space by the time you leave here, then shame on you. We're going to talk about long-term life in space. Now, I understand that the Ortop Challenge this year was about having to live in space for a long time, whether it's in orbit or Mars or a habitat or something like that. And I want to give you an idea of what the space life is really like, kind of give you some tools in your toolbox as you think about what you would need. What would you need to pack? How would you need to prepare? How would you need to train? How do you pick people? And so it's kind of a passion of mine anyway. I'm a medical doctor. The human body in space is really what I love to do, what I love to study, and what I was really happy to experience. So that's kind of what we're going to emphasize tonight. But for the most part, I want everybody, again, to take what you learn here, think about it as you apply it to your project. And like I do go places for inspiration, well, I should take the places you go for inspiration. Here's one of the first places I went for inspiration. Now, I know there's some really young people here. Okay, so hopefully most of the people can recognize the person in the upper right. Prove it.
What's his name again?
I know his name. You're killing me. Okay, so James February Kirk, captain of the Enterprise, so Star Trek debuted in the late 60s, and it really started an empire. My grandmother was watching Star Trek, and I was watching it with her, and it was really the guy in the lower right there that intrigued me, because you know, Captain Kirk was the captain of the starship, and you know, he was like the captain of any ship, as you could possibly imagine. Whereas Bones, Dr. McCoy, had to really think about what species he was encountering. And when the captain said, Bones, go help this, whatever, entity, he had to think, okay, where are they from? What planet? What species? What's their anatomy like? What's their physiology like? What's their life like? And so the very idea that there was a kind of medicine that was not of this world, that was space medicine that you really had to think differently about was incredibly intriguing to me. And so I really kind of caught that bug very early on. Now I'm going to take you back a little bit, because certainly as we talk about space life, this is not the first time we've had to talk about living away from home in uncomfortable places to explore for long periods of time. And so can anybody name the gentleman in the upper right? I see a lot of young hands. Yeah, go ahead.
Me?
Yeah.
George Washington?
You're telling me again. No. Think about exploring on a ship. I mean, they all wore white wigs, so yeah, I catch some slides there. Anyone else? You can just shout it out.
Columbus. Christopher Columbus.
Okay, so how about the adults? Good, thank you. So this is Captain Cook. And Captain Cook was actually a lot of the inspiration for Captain Kirk. And what Captain Cook did in his voyage of exploration was a lot of the inspiration for Star Trek. Everything from long missions, a 5-year mission, and a kind of a directive in a way that at least the purpose was to be kind of non-interference and not to just be subjugating populations that they found, but to really explore. And that's where a lot of Star Trek came from. It's really quite remarkable. Okay, so I showed you Captain Kirk and Captain Cook. I showed you Dr. McCoy. Who do you think the gentleman is on the lower right? A doctor. And that's about as far as I expect to get. Because no one's ever heard of this guy.
George Washington.
No. Again, this is actually... Yeah, okay. This is William Brown Monkhouse. He was the ship's surgeon on the ship Endeavor. So it wasn't the Enterprise, it was the Endeavor. And he was in charge of crew health. And one of the revolutionary aspects of Captain Cook's voyage was that particular attention to the health of the crew. Now, this was at a time when exploration and trade was associated with about a 50% mortality rate of a single mission. Say, Dutch East India Company would send a ship out, and about half the crew would die of scurvy and other diseases. And that was acceptable mortality back then. It was unbelievable. But they really wanted to do better. Nobody died of scurvy on this trip. It was quite revolutionary. Now, they weren't the first to use treatments, vitamin C containing foods about it, but they were the first really to apply it on a large basis on a complete mission. They did have a problem with intestinal disorders, dysentery, which there was nothing they could have done about at the time, but still they did incredibly well. Nobody died of scurvy, and Captain Cook became known throughout the Admiralty as really watching out for crew health and incredible success to the mission that came from that. Healthy crew, happy crew means a successful mission. They are more likely to do what you sent them out to do, so it just made sense in every way, shape, and form to be a lot more disciplined about crew health. And this is something that has propagated over the centuries. It put the British way ahead in exploration, naval warfare, and everything. And so we have propagated the notions of exploration from British maritime history tremendously. All of our space shuttles were named after ships of discovery. So this is, for instance, the Space Shuttle Endeavor, named after Captain Cook's Endeavor. Now, Captain Cook's second voyage, he had three, actually had a ship called Discovery. And even that wasn't the first discovery. Henry Hudson's discovery around 1602, where he took this one north and actually discovered Hudson's Bay from the New World. Unfortunately, there was a mutiny, and Henry Hudson was never seen again, but the ship was awesome. Fortunately, we haven't had mutinies in the space program. But there's Captain Cook's discovery in 1774. Captain George Vancouver's discovery in 1789. We all know the city of Vancouver, or two cities of Vancouver, named after Captain Vancouver, who found this area, or actually explored this area in his ship Discovery. FYI, this was actually launched as the Bloodhound, as a whaler, and the British Admiralty converted it to a ship of dedicated exploration. And you can see that name just continued to propagate, the name Discovery for ships over the centuries, really. And the HMS Discovery, actually, let's go to the RRS Discovery. The HMS Discovery was built to purpose to sail to the Arctic. The RRS, the Royal Research Ship Discovery, was built to go to the Antarctic, which it did with Robert's Falcon Scott. And it was an amazing thing because, again, at a time when there wasn't a lot of spare cash around, they sunk a lot of money into pure exploration. You guys keep your fingers crossed here. And it was a wildly successful mission. Now, let's see.
Gone again.
It's on again?
No.
Okay, I just want to be sure you're all seeing the same thing I am.
This is weird. Now there's bugs on the screen.
Bugs on the
Now there's
screen.
lasers. Well, probably glitching your computer.
I don't think it's my
There's
computer.
lasers.
That is kind of weird. I think that I'm starting to suspect a projector now. So I'm wondering,
Is this a slide?
okay, as long as you guys are aware, that's what I'm wondering. This was the Space Shuttle Discovery. So again, we named this Space Shuttle after a long line of ships called Discovery. So the legacy of exploration is really there. And I was very lucky to fly on the last mission of this Space Shuttle Discovery. So it was the fleet leader. We actually racked up 365 days in space while we were up there. And that is the 365th day. We were only up for a couple of weeks on it, but an amazing ship with an amazing legacy. So now we fast forward and talk about space exploration. This is my first launch, 2009, and we were getting ready to launch on the Soyuz. In the middle of Gennady Padalka, my Russian commander, on the left, Charles Simonyi, who was actually a paying tourist, if you will, spaceflight participant, but basically a tourist. He paid about $40 million to fly with us. And we chuckled about that because we're getting paid to do all this. And he had to pay. But he was actually on his second flight, which is quite amazing. And he was very good. He flew as a second-time tourist, but the guy is also a computer scientist, PhD, in computer science and a rated jet pilot. So he was very at home.
Bye-bye.
And of these 3 crew members, I was the least. All right, so.
No signal.
All right, I am going to take a chance and unplug and replug. And say some incantation here.
In that photo, are you in the middle?
It's a window.
Excellent. I was on the far right side. Okay, we're gonna fast forward here because I don't want to do anything. Here we are. Okay. All right. Again, first launch. Hope this works. Here we go. Now, this is the Russian Soyuz launching out of Kazakhstan near Baikonur. So you're in the middle of the Kazakh steppe. And it's just a straight stick rocket with a capsule at the top. And when the thrust of the rocket equals the weight of the rocket, basically, it lifts off. It's very gentle. You can barely tell that it leaves the pad until you see your clock starting to count up and you start to G-forces build. And it's just an amazing thing to see. You almost feel the vibration in your toes when this thing happens. And us on the inside, we're covered with shrouds, so we can't see outside at all. So our view is very good. We're just watching our displays, but a very reliable, very robust, very safe vehicle, as safe as you can get doing this kind of thing. And it'll go up for about a couple of minutes or so. Those 4 strap-on boosters separate, and then it smooths out a little bit and heads on up to orbit. Now, we have to go from 0 to 17,500 miles an hour. That gives us orbital velocity. That's how we stay in space. If we go too slow, then we decay our orbit and we re-enter. If we go faster, our orbit raises. And we did it in about 8.5 minutes. And it's quite a ride. It's, like I said, a fairly gentle ride. And interesting thing is that this is the same launch pad that launched Yuri Gagarin, the first man in space in 1961. Yes, they're still using it. Why? Because it works. Simple, reliable, very simple mechanical actuators, nothing real sophisticated about it. And again, the thrust of the rocket equals the weight, and then those support cantilevers just fall away. And you can actually launch 2 rockets in a day from this launch pad. They have done that. So it's really quite simple and quite elegant. We have a lot to learn from our Russian counterparts. Now, my second launch was very different. Okay. So this is the Space Shuttle Discovery. This was in 2011. And we had 3 really big engines down there and then 2 strap-on solids. And when those fly, it's just like being kicked into the sky. It's very shaky and rattling, to be honest. Because you have all this thrust that's offset from the center of mass. And this is a view from the booster, and then this is a view again from the ground looking up at the plume as it builds. So either way, you're still having to build a velocity of 17,500 miles an hour. This is our separation from the solid booster, which is now falling to Earth while we continue up into orbit. And because now we're just left with our 3 liquid-fueled engines, it actually gets a lot smoother. So that happens a little over 2 minutes into flight. We have another 6 minutes to go. Again, about 8.5 minutes and 45 seconds. We've built that velocity of 17,500 miles an hour. Now this is a picture of the Discovery as it went up, and again, the forces that it takes to accelerate that fast, that's where the danger of spaceflight really is. It's in the launch and then in the landing, because you have to lose all that velocity to come back. So the forces associated with that are really where our hazards are. Once you get up there, 8.5 minutes, the engines shut off, and it's really abrupt. There is nothing gradual about the transition to being in space. So you go from weighing about 3 times the normal body weight to nothing, just like that. And it's a very seminal moment in an astronaut's career, especially your first flight. because all of a sudden you're feeling this rush of fluids to your head, your balance system is totally out of whack, you start to float, everything that you thought was secure starts to float around you, then you see the Earth, your home planet for the first time, and you're trying to make sure that your spaceship is still good and not leaking and that you're going to continue the mission. All of that happens in the first few seconds. It's just one of the most incredible moments in a new astronaut's life, and I will never forget it for sure. This is, what is this?
ISS.
Yeah, ISS, International Space Station. And this was taken actually by the Space Shuttle Discovery, by me, actually. It was kind of an interesting coincidence because we had a Japanese cargo vehicle, that's kind of the orange and silver soda can in the middle, and then we had a big white European transfer vehicle with kind of the excellent solar panels on it. We had 2 Soyuzes and a Russian Progress cargo freighter, and then when we docked to it with our space shuttle, we made the biggest pressurized volume in the history of spaceflight. I think that record is going to stand for quite a while. And so the station is actually quite large. When you're starting to do your rendezvous with it, you see it from about 200 miles away as a bright star, and you just get closer and closer, and then you're just aghast at how big this thing really is. It's quite amazing. And this is what I like to call the real estate listing for the ISS, but it gives you an idea what characterizes this platform for us. When you hear us talk about spending 6 months or even a year up here, this is what we live in. So it's only about 240 nautical miles overhead. Not that high, right? So when you talk about outer space, we're not that far away. Remember, what separates us is more speed than distance. You know, you have to work very hard to build that 17,500 miles an hour to get there. But once you get there, you're not that far away, but you're always moving. So it's really more of a speed barrier that separates us from y'all on the ground. We're weightless, basically microgravity or free fall, or free floating as you call it. And that's why we're there, because it gives us a laboratory to study things in weightlessness. Sea level pressure and atmosphere, which means 20% oxygen, 80% nitrogen, and 14.7 pounds per square inch, if anybody cares, but it's basically the same air in this room, pressure and composition. And it's big, about 35,000 cubic feet. If somebody's trying to sell you real estate in space and they quote something in square feet, doesn't matter, there's no floor. All right, square feet almost means nothing up there. So really, you're looking at the volume that's habitable. Habitable volume is what we worry about. The views are great. There's great waterfront views. And like you might see the eastern seaboard at one point, then the Mediterranean and the South China Sea. So you can see pretty much all the waterfront on the planet. And it's close to public transportation because pretty much it's the only destination in low orbit right now, so all the cargo ships and human carriers go there. We have 6 bedrooms, 2 bathrooms. It is sort of furnished because there's no chairs, because nobody sits, there's no gravity. And we kind of sleep in sleeping bags just tacked to the wall. Anyway, the other good thing about it is a semi-closed loop environmental control life support system, which means we can recycle about 85% of our water, and we try to reuse as much stuff as possible. We'll talk about that a little bit more. When you get into space, you change a lot because your body is in a place it's not used to being at all. This was day 1 for me on the ISS, and it looks like there's a definitive up and down, but that's only because of what the camera is showing you. There really is no up and down. And when you get into a big volume, you feel like you're falling in every direction. So if you were to zoom in on my right hand there, you will see white knuckles, because I'm holding on as tight as I can. I have 2 feet under foot rails, and I'm holding on to my friend Koichi Wakata so that I don't fall or lose control. And it's just an incredible sensation to feel like you're falling in every direction. But with time, we become very different creatures. So here, first of all, my hair's a mess. But you can see that my body is no longer straight and rigid like I was before because I was trying to be as Earth-like as I could. This is more space-like. You're kind of slightly bent in all of your major muscle groups. And I'm actually floating in the middle of the module. I'm barely holding on with one hand, and most of the time I've actually let go. I'm just floating there, and I'll grab the handrail just to adjust my position. And I've got stuff on my leg, just bags with Velcro dots on the Velcro pile on my legs. And that's just kind of what we become. We become basically 3-dimensional creatures that are very at home navigating and figuring out their position sense and moving big things in a weightless environment. And it is a very methodical process with milestones. You can kind of track people's adaptation to zero gravity, both from the standpoint of the physiology and how they do behaviorally. It's quite amazing. One little point I like to make is that things become opposite there. On the ground, we walk with our feet and we carry things with our arms. Right? Out there, it's kind of the opposite. Your legs don't really do much for you. Your feet don't do much for you because, again, there's no floor, really. So we carry things between our legs and we'll pull ourselves along with our arms and just impart some motion, and we'll keep going until we hit something. So there's nothing that's going to slow you down. So you get to the point where you can put, these are 20-pound food containers. So I got 60 pounds just held between my feet. I can rock it from one side of the station to the other and land on a dime very gently. Everybody gets to be able to do that. So we just become these very different creatures that behave and navigate totally differently than we do on the ground. If you have a lot of hair, like my friend Karen Niger, one of my classmates actually, you really got to be careful of it, to be real honest, because this is going to go everywhere. So you definitely don't want to get near any machinery. You don't have any open rotating machinery, which is a really good thing, well, except for the fan blade. So you have to be careful with that. And a lot of the women in our cadre will wash their hair and just kind of leave it out like that to dry, because it dries pretty quickly, because it just doesn't hang on itself. And of course, we recover the water and condensate and sterilize it and use it again. This is what we do up there. It is a science laboratory. It's a very well-equipped science laboratory. And every day you're doing experiments pretty much all the time. So you can see in the upper left there, that's kind of this neutral body posture. That's what the body is like in zero gravity. Again, kind of a slight bend of all the muscle groups. And I'm working with a metabolic gas analyzer so we can check lung function. The lower left, my friend Dr. Bob Thirst, that's actually, he's got a syringe where he's just injecting gel on there, so it's not as horrific as it looks. But we were doing a sleep study with electroencephalography, looking at the brain waves cap on one of our crew members. In the middle, Dr. Kate Rubens, she's a world-class virologist, actually, who we plucked away and made an astronaut, and she's doing an experiment on cardiac cells. And upper right, my friend Frank DeWinna is using a freezer, which gets to about minus 100 degrees centigrade. We can freeze samples of serum and tissue and urine and whatnot and bring down for analysis. Now, in the lower right is a glove box. And remember that you're in zero gravity, so you can't just leave little particles anywhere, because they'll just go in the atmosphere and you're going to breathe them and they'll be up your nose and all that kind of nonsense. So we contain everything that might shed particles in glove boxes. Okay. Keep my fingers crossed again. So I'm just going to talk really quick. And normally I give like a 2-day lecture on human physiology in space. I've condensed it down to one slide for you, which for me is very difficult. And this is a picture that we made when I was running the NASA Human Research Program. My staff thought it was too creepy to use, so we didn't use it. I'm the only one who uses it, but I think it's great. And what I'd like people to know is that there's a broad set of physiologic changes, a constellation of changes that happens in the body in weightlessness. So first you get a fluid shift from your legs up to your chest and your head. And actually you will lose about 15% of your blood volume and 50% of your red blood cells. I'll keep talking here and we'll see if that settles out a little bit. Your sense of balance, position changes radically, and your heart and blood vessels change radically. And all of these things make you better for spaceflight. They make you better for weightlessness. And it's your body basically adapting to its new environment and optimizing its performance. It's a really amazing thing. And we didn't anticipate any of these things. One thing we did kind of anticipate was the loss of muscle and bone, right? We know that once you get into zero gravity, you unload your bone and muscles, and so they start to weaken and lose density and strength. So that is something that's not a good thing. It's fine for zero gravity, but not if you want to come home, which we all do. Your body changes shape. Your abdomen, your waist gets smaller. Your chest gets a little bigger. You get a little taller. Sounds great, right? You do pay for it in various ways. But that is all, again, a space flight normal. It's really quite amazing. We actually do a lot of blood draws up there because we're doing analysis for metabolism and physiology studies. As the onboard medical officer, I took other people's blood, and I also had to take my own blood, which is actually not that hard. But the point being, you can do almost any procedure in space that you can do on the ground, as long as you manage your stuff in zero gravity. You can't put a test tube down here, because it'll float away. You gotta put it in a special test tube holder, or it's gotta have Velcro or tape or something like that. So learning to manage things in zero gravity is really all you need to do to adapt a normal Earth procedure to spaceflight. It's not that hard. Long duration anywhere means away from Earth, and you have to be very careful of how you handle normal body functions and body products. So this is our zero gravity toilet. My friend Koichi, and that long hose has a funnel at the end, and that's kind of where what we pee into, right? So if you're trying to pee in a potty right now, you know the gravity pulls it down and just falls neatly and nicely into the potty. But there's no gravity, so that ain't gonna happen. You need airflow. You have to have something to entrain the fluid, so we use airflow. So there's actually a fan that runs through that hose, and you turn on the fan, and as long as you got a suction going, you can pee in that hose and pee in that funnel, and that's where the pee goes. And accuracy is everything. Aim is important. It is bad citizenship to miss, because that all goes in the atmosphere, which we all share.
Gross.
So you have to be very careful. And believe me, it works just fine. And by the way, that is a Russian toilet. It's the one in the middle there, on the right side, the little silver canister and everything. That's what that hose attaches to. Why? Because they build by far the best toilet for spaceflight. There's a lot of things they do just a lot better than us, and that was one of them. What's really more interesting, though, is what happens to the water after that. Now, it costs a lot of money to launch a pound of anything, and launching water is very expensive. So if you can reuse the water, you really want to do that. So we have our own water cycle up here, just like we do on Earth. It just happens a lot faster. So if you pee into that hose, it's going to go into a manifold that collects it, goes into a distillation and purification assembly, and then gets minerals added, gets tested for microbial content, carbon content, and eventually it'll show up in your coffee the next week. So as my friend Don Pettit, who's also from Oregon, by the way, says, we turn yesterday's coffee into tomorrow's coffee, and that saves you 85% of the upmass of the water. And you will have to do that anywhere you go if you want to live long and live large in space. So that's just one of those things. And actually, my crew was the first to use this, to drink the potable water reclaimed from recycled urine. So that was a big day for us. Well, it was a big day for most people. Actually, as the onboard medical officer, I had been drinking it for days ahead of time just to make sure everything was okay. So it's one of our time-honored duties. See on the left there, those are the two racks that are needed to do just that, to purify the urine. And actually, one of those, there's a sub-rack in there that will crack the urine into hydrogen and oxygen, and we can breathe that oxygen. And we can dump the hydrogen overboard because we don't want explosive gas around. But that's the technology we develop on the International Space Station. And more importantly, in the lower right, we use a lot of that water to rehydrate food. Right? I think that's green asparagus or something. It tastes a lot better than it sounds. But it's an amazing thing to be able to have additive access to all the water you want, all the fluids, and all the food. And that went tremendously positive for the health of the crew. As of the time we started with this new system of water reclamation and the food dispenser and an exercise countermeasure set, I'll show you, the health of the crew took a quantum leap forward. So speaking of exercise, I mentioned that bone and muscle get weaker, and because of that, we have to exercise 2.5 hours a day to keep bones and muscles strong. And now we like that, actually. It feels good to load yourself, and it's at a time where the ground isn't going to be calling you all the time, asking you about science experiments. So psychologically, it's a big boost for us. Physically, it maintains your bone and muscle. It keeps you strong enough to be able to come home. So on the left side, I'm actually doing resistive exercise. We have a machine that gives us really big loads to pull against and to push against, and that's really helped us. On the right side, Koichi-san, my crewmate, is on a treadmill. Remember, there's no gravity, so no weight holds you down to the treadmill. So he's wearing a harness with straps that holds him down in place. And you really have to totally learn to run again. But once you do, it actually feels pretty good. Okay, short switch. And let's see if that pops back. I'm almost prepared.
There's a love bug.
What you just saw I'll let you, because it did seem to work. I can't. Try it. Anything else? Although I'm actually not supposed to do I knew that, and whatever you did seemed to help. What you're seeing flashing on and off there is bicycles. So we've got 2 bicycles that give you a good cardio workout. So treadmills, bicycles, resistant exercise, all of those work together. Okay. So, having exercise really helps us. Again, 2.5 hours a day, it feels good. I will say that even if you're on the moon, where there is some gravity, it's only about 1/6 gravity. So you're not weightless. We know that you're able to walk around a lot. But you will definitely need some kind of exercise up there also. Because 1/6 gravity is still not enough to maintain bone and muscle like you'd like to. All right. All right. I apologize. I'm just going to keep doing it this way because I think that is less risky. You guys tell me when we get to the treadmills or to the bicycles.
Almost there. Next one.
Good. Well, I wanted to go to the next one. Okay, so we get asked a lot about the food. This was actually the time when we had a visiting shuttle. So we had 7 more crew members to add to our 6 on board. So there were 13 of us, and inviting 13 to dinner around a real tiny table is no problem in 0G because you can stack people and float over the table, no problem whatsoever. So it's a really good time. We really enjoy our chow there. And actually, you can see I'm holding a little round thing down there. That's actually a moon rock that the Apollo 17 crew brought back to Earth, and they sent it up to the station. We were celebrating, I guess it was the 40th anniversary of the Apollo moon landing, and it was kind of cool to have that there. So we played with the moon rock a lot. We also played with our food a lot. And this is kind of a close-up. It shows you what the food is like up there, and the food is good. Don't let anyone tell you the food isn't good. Because we have so many countries involved now, we have Japanese, European, Russian food is actually very good.
Italian?
We do have Italian, especially when we have an Italian flying. We even have an espresso machine up there. Estimating for 0 gravity. It is not easy to make an espresso machine for 0 gravity. So we eat well. Gone are the days of squeezing mashed potatoes out of a toothpaste tube. And sometimes we're up there actually enjoying crab and truffles, and the ground thinks that we're eating awful stuff, so it's not a problem. One of the things I will tell you when you're off for a long period of time, having personal space is really important. And each of us is actually kind of working in what we call our offices there. My computer, Koichi's computer, each of us kind of had our own little place with our own little gear there. And that ended up being really important because you always knew that stuff was there when you got there. And personal space, even if it's tiny, even if it's just a little bit of stakeout real estate in a common area is quite important. And we'll talk a little bit more about that as well. Soyuz entry. Now, this is what the Soyuz looks like when it's coming down. So our mission is done, 6 months have gone by, we're coming home. This is a computer image because we don't have a chase plane. Now this is a real image from inside the cockpit. And you can see the plasma cloud is glowing out there, and our heat shield is coming apart and sparking. And the window is actually melting, and the right side is the leading edge, so it's white hot. It's actually getting thinner there as the glass starts to run to the left side, the trailing edge. And the glass kind of smokes over eventually, it becomes useless. But it's hot. Because remember, we have to go now from 17,500 miles an hour to 0, and we do all that by frictional drag with the atmosphere as we come down. So that friction causes a lot of heat, and that's what causes the melting there. Now, a little bit more detail on in-cabin view of the Soyuz and computer-generated view. We separate just at the mouth of the Mediterranean, so you can see us coming over the Mediterranean there. After a deorbit burn that slows you down just enough to dip into the atmosphere, you start doing this. So that's the frictional heating, and it actually does get pretty warm inside, but not nearly as warm as outside. And that glass blows away, so there you can see it's nice and clear now, and the G-loads are really building. Now, it's a very high altitude chute opening, so it's a very high altitude, or a high opening shock. Now, you can use those 4 Gs that you're feeling as you're going down to tighten your straps, because it really hunkers you down into your seat. We're coming down on a single parachute. You can see a search and rescue helicopter there. And so now, by now, we know we're going to land and we're going to be fine, but our seats are going to change just like that, and they'll put us in a position that handles that landing impact a lot better. We hit the ground at about 9 meters per second or so, and you'll see a big flash just before we hit. Bang! So those are soft landing engines that cushion the fall a little bit for us. And there it is again. So that big cloud of smoke and dust, and that's what it looks like from the inside, is actually the rockets, the backwash from the rockets and blowing dirt, because it just makes a big crater blowing. But it gets you down safely. It's an amazing little vehicle that uses the combination of the retro fire, the parachutes, the seat angle, the seat stroke a little bit, and those soft landing engines to get you down safely. It's really quite nice. Contrast that with the shuttle. The shuttle, of course, looked a lot like an airplane, a glider, and so it landed more like an airplane. So the launch was very rough, the landing was very gentle. So it's kind of opposite of the Soyuz. And when we landed, actually we had to punch through a cloud deck. It was kind of different. We also had a crosswind. There were a lot of challenging conditions for us. Steve Lindsay, my commander, just brought it in magnificently. You can see us gurgling a little there from the winds. The gear comes down only about 300 feet or so above the ground, so you really want to be sure you get that down. But it lands very nicely, very gently, and one difference though is that we're actually seated upright on the space shuttle, unlike lying down on the Soyuz. And because of that, we have less blood, we have fewer red blood cells, as I mentioned. We actually are a little bit more prone to what's called G loading, and so you can actually pass out from just being at 1 G when you're standing straight up because you're not used to it. So it's we've had to use G suits for all the shuttle flyers because of that problem. So Soyuz kind of mitigates that. Landing is always great. This is my landing, and after 199 days in space, landing in the Kazakh steppe back there again in the middle of nowhere. It was just really nice to be home. It was great to smell fresh air. It was about 40 degrees outside, sunny as you see, and a lot of my friends were there. It was just an amazing thing. And you land in the middle of nowhere. They recover you. They recover the capsule. There's medical tents where they'll check you out, get you changed, do some science and medical checks. And within a couple hours, the desert is clean. Everything's gone. These guys are just incredibly efficient at what they do. So that is walking through an ISS mission. Now let me tell you a little bit more about where we are now. These are spacecraft that are being built right now. They're not PowerPoints, they're not computer images. These are real spaceships that are being built right now. So on the left side, the Boeing CST, otherwise known as the Starliner, and the SpaceX Dragon, both of those will be carrying crew members to the space station by next year. And that's a pretty amazing thing. So we have contracts with both of these guys. We work with them every day. That's my assignment right now, is to work medical issues with the commercial crew. The upper right, Sierra Nevada Dream Chaser, we signed with them also to deliver cargo to the station, and there will be a man-rated version of this sometime in the future. And then Blue Origin, which we have some agreements with, but they're doing this pretty much on their own. The New Shepard will actually be a human carrier for low Earth orbit as well. So that's 4 new spaceships being built here in the U.S. There's never been a time in history like this. It's really quite amazing. And what I think is more exciting is when you look at the global picture, it's a very international effort. And here you kind of see what the new spacecraft are, and they're very capsule-oriented, right? So we are building a mini shuttle, the Sierra Nevada Dream Chaser, but the rest are all capsules. They're very reliable, and it causes us to separate the crew from cargo, which is a lot safer for the crew. So you can see the Soyuz is over there on the right, and that's what we've been flying to the space station for quite a while. And some of these you'll recognize. The Orion is the big one over here on the left, which will go beyond low Earth orbit and potentially help us to get to the moon and further. But very interesting, you see the Boeing capsule, which will take crew to the space station very soon, the Starliner.
But there's a lot of other things going on as well. The Russians are going in a new large capsule. The Chinese have the Shenzhou. And then you have the SpaceX Crew Dragon in the middle. And very interesting, to the right of that is an Indian capsule. The Indian Space Research Organization, ISRO, has their own boosters. They've got pads, they've got all sorts of infrastructure. And they've made a declaration that they're going to be flying crew members by 2022. Their own crew members. So they'll become the fourth country to fly people in space. We find the US, Russia, and China. So it's a global effort, and it's happening at a very brisk pace. And low Earth orbit itself, we've got the ISS, but we expect to have more low Earth orbit platforms in the very near future. So the opportunities are going to be growing. And this is an artist concept, but this is hardware that we've actually been building along with Bigelow Aerospace. It's actually inflatable modules, which we developed at NASA and transferred this technology to Bigelow. Now, we're going to wrap up by talking about leaving the Earth vicinity. What happens when you want to leave, and what are the factors at work? One is radiation. There's a lot of radiation in space, and when we get away from our magnetic fields, you can see the kind of the blue shields around the Earth, are geomagnetic fields, the Van Allen belts, which protect us from a lot of solar radiation and even deep space galactic radiation. Once you get away from the Earth, you're bathed in this stuff. It's charged particles, electrons, protons, some heavy nuclei, even like iron. And those can be very damaging to DNA and other macromolecules and give you a higher risk of cancer and whatnot. So that's something we always have to be mindful of and check everybody's radiation dose. Communication latency, what does that mean? Well, the further you go, the longer a radio signal has to travel to get to you and back. Speed of light and the speed of radio transmission is 186,000 miles a second. That sounds pretty fast, but that means with the moon at 240,000 miles away, it's going to be about a 3-second round trip for a radio signal to get back and forth. And when you're looking at Mars, which at its closest approach is 35 million miles, and furthest is 220 million miles, the way the planets move around, at its furthest approach, or furthest distance, it could be 40 minutes round trip for a radio signal, 22 minutes one way. So there will be no more real-time conversations. There'll be no virtually controlled real-time call robotics. Nobody's going to guide you through a procedure that you don't know how to do real-time. So that's something you have to think about with deep space. Now, I mentioned the Orion Vehicle. This is it, and this is something that we will be using generically for any deep space destination that we want to get to. It can take us to the moon. It can take us to a orbiting lunar space station. It can also dock with a habitation module and even go further, or it can take people to a trans-Mars ship. And we've actually tested this capsule a couple of years ago on a Delta IV Heavy. We'll be testing it on this booster system in the next couple of years, the Space Launch System, which is this massive rocket, which will be the largest rocket in the world once we field this thing. And I was actually at the Marshall Space Flight Center looking at some of the hardware just a couple of days ago, and the sheer scale of this machine is just unbelievable. It's fantastic. One of the things that we're considering is the Deep Space Gateway. We're considering actually very seriously. And this would be a station in the vicinity of the moon, where we will send a few people up there, and then we'll be able to launch missions easily to the moon's surface, and then back up to Gateway again. It gives us like an advanced forward outpost, and it actually becomes very efficient for lunar exploration. So that is one of the biggest things that we're spending our time on right now. Now, if you want to go further, you really need to be ready. One of the ways that we get ready is by studying analogs. Now, this is what we call the deep space habitat. And this was out in the Arizona desert, actually, for quite a while. We would put crews in here. But it's very similar in size and shape to what we might be able to send to Mars. I'm not showing you a picture of the inside, but on the inside, it looks very much like the habitat from the movie The Martian, that you see that with
Yes.
Now it's kind of patterned after this habitat. By the way, we've moved this habitat to Johnson Space Center, and it's in a very large building, just sitting in the middle of the building. And we lock crews in there for like 45 days at a time. And believe me, we work them hard, we give them plans, we talk like we're mission control. We even introduce a comm latency. So we'll send a message, and 8 minutes later, they'll get it. And then they can respond, and they just know that it's going to take a while, so there's no real-time comm. And they literally come out and say, I forgot where I was. So it's quite a useful habitat for us. But we want to get ready for this. And when we send people here, it will be for long periods of time, because you really don't want to go through all that trouble, all that hazard and risk to send people there for a couple of days or a couple of weeks. It's going to be many, many months, if not 1 or 2 years. So that's what we're getting ready for. You have to get hardware ready. You have to get logistics, food, tracking, communication, all of those systems ready. But most importantly, you have to get people ready. And that is one of the hardest things. And I really like what Roald Amundsen said, the very famous polar explorer. The human factor is 3/4 of any expedition. And even back then, they were pushing the edges of their technology and planning and food sources and everything. But he understood very well from experience that keeping your crew healthy, happy, and provided for means they're going to perform better and make you better able to support your mission. I'm a Disney freak. If you guys haven't seen Treasure Planet, you should. But Dr. Dilbert Doppler, I think, said it best. There are worse remedies than a few character-building months in space. Being months in a place where you're out of your comfort zone, you have to learn to get by with whatever is there. You have to learn to get along with whoever is there. You have to learn to work together if you want to come home. And I think he summed it up brilliantly right here. Now, when I was you guys' age, most of you young people's age, there were 9 planets. That was it. Yeah, life was good, wasn't it? And then they demoted one of the dark planets. Now, yeah, I mean, there was a good reason. They demoted it, and I say they, because it wasn't NASA. How do we take all the flack for it? It wasn't us. But the idea that there were other objects outside of Pluto that were even some bigger than Pluto, that's an exciting thing. All that got lost in the naming thing. Well, now we know that there's thousands of planets around other stars. I mean, it is a new era. There are thousands of planets out there. Planets are more the rule than the exception around other stars. And we used to think about that and fantasize about it, now we know that, which is really amazing. I'm just highlighting the one system, the TRAPPIST-D system, because it's close, fairly close, 40 light years away. Now, a light year is 6 trillion miles, and this is 240-ish trillion miles. That's an awful long way. That means you really need to learn how to fly faster than we know how to fly. We have no way to get there right now. But it's very tantalizing to see these planets, and some of the new telescopes and machines we're building will be able to look at the atmospheres of these planets and look for signatures of life. So it's very likely that we'll find evidence of life long before we'll be able to get there, because there's thousands of target planets to look at, which is really amazing. So somewhere out there are alien landscapes that look like this. And if there's any stronger magnet for us to explore outwards than this, I don't know what that would be. Okay, I'm going to stop here. This is actually a picture for Tim Todd, who's not here. But this is last year's eclipse, which I got to see from an airplane at 40,000 feet, which is really cool. Okay, so we'll stop here, and we're going to arrange some questions. Okay.
All right, so before we start lining up for questions, if any team needs to leave, please use the upper exits behind you. There are 2 staircases. We are going to line up for questions single file in this staircase. So go ahead, team members only, no adults. You guys go ahead and line up for questions. And if we have time, there will be an opportunity to take photos at the end. We'll line up on the other staircase for that.
You're on the outside.
Walking There'll be people on the stairs.
Do you want to?
You ready?
No, you can go. He's going to go over there. He's going for questions.
In space, do you miss your family?
Yeah, actually, there's nothing you miss more than your family in space. I mean, I didn't really miss that many things on Earth, but I did miss the family. So, yeah. Just like the old sailors. Is that a team question?
How do you communicate with your family in space?
So on the space station, we have the luxury of internet protocol telephones that go through our satellite network. There's 6 telephone lines out on the space station, believe it or not. So I could literally dial any number, any phone number on the planet that I wanted to. So I talk to my wife every day, and I talk to my kids periodically, and then I got to do a video conference with them. And now they can do video conferences every day. So it's pretty good.
What do you do in space for fun?
What do you do for fun? It's all fun. I mean, frankly, none of us ever got bored, at least not on my flight. I mean, flying and floating and looking at the earth and playing with your food, and I mean, shoot, who wouldn't like that? We do have some stupid astronaut games that we play at night, but I'm not going to talk about it. That's when the cameras go off, and
Oh, like what's the longest that anyone's ever been in space?
So the longest mission was done by a Russian cosmonaut named Valery Polyakov, who's actually a physician, somebody that I know, and that was 438 days. That was on the Mir space station. I actually saw him the day he landed, and it was amazing.
Are there ever problems with space junk?
Yeah, there's big problems with space junk. Most of the space junk is really tiny, and it hits the station all the time, and you can see that the outside is almost like sandblasted. It's cratered with little tiny pits. But we do worry about getting hit with bigger things, and every once in a while, if we see something on radar, we have to move the space station out of the way of it, which is a big deal. So it's one of our biggest worries.
Do you ever get tired with space?
Do you ever get tired of space? No. I mean, I have a big family, 5 kids, we're a very tight family. Day 199, I didn't want to come home. I wanted to stay in space. And I wanted to get back as soon as I could. I was already assigned to another mission when I landed, so no.
Are there any airlock problems?
We have not had airlock problems, but it is definitely something we worry about because it's a big seal that if you can't seal it for whatever reason, whether there's impurity or the seal breaks, then you got a big hole in your space station. So we worry about it. We haven't seen it. Nothing like what happened to Matt Damon on Mars.
What would happen if you tried to light up a candle or use fire in space?
A really good question. So. In space, there's no gravity, which means there's no buoyancy. Buoyancy is when things float. Heavier things sink in lighter material. And a candle burns because of buoyancy. So oxygen comes in, it burns the oxygen. A candle flame has a top and a bottom, very definitive, and it's very much about gravity. It burns the fuel, oxygen comes in the bottom, and it circulates. If you just light a match in zero gravity, it'll burn the oxygen around it, and it'll go out. Certain fuels you can actually propagate a flame along, but fire behaves very differently. But if you blow on it, even just a little, it flares like crazy. The behavior of fire in space is really kind of wonky and kind of amazing. Fire is dangerous. It is one of our biggest worries up there. And one of the problems is we worry about pockets of increased oxygen concentration because of that low buoyancy. Oxygen, if it's introduced into the atmosphere and not blown around enough, it can just sit and concentrate in one place. So high oxygen environment is very risky for us.
Were you nervous on your first flight in space?
Was I nervous? Yeah, a little bit. I mean, if you're not a little bit nervous, you don't know what you're doing. But we're very task-focused also. So after years of training, I'm finally there. I have a job to do. I have duties. I don't want to mess up, and that's kind of where your main focus is. My family was a lot more nervous than I was. Yes?
Is it a real problem on how much you can bring to space, like food, water, and air?
Yeah, it is. That's why we recycle all the water that we can, and we try to lose as little air as possible. When we do a spacewalk, we have to depressurize the airlock. We have to open the door and let the air out. Instead of letting all the air out, we pump it in. We use a lot of power to keep the air. So everything we can do to minimize the loss of water or air, we do. So the more you can save and recycle, the better you are.
What are the main foods you eat in space?
The main foods we eat, they're dehydrated, they're canned, they're foil packed, and everything is highly preserved because it has to basically have a shelf life of months to years. So it's not a lot of fresh food. Only when a cargo vehicle comes and we get a couple of apples or something like that, but mostly heavily preserved canned foods and freeze-dried. But it's very tasty, I think.
When you eat, what does the food taste like?
Interesting, to us in space, food tastes a little bit bland, and so we use a lot of hot sauces and a lot of peppers up there. Spicy foods tend to taste better up there to us. But mostly, the food like macaroni and cheese, tastes just like macaroni and cheese. It's better with a little bit of chili sauce.
How long is the food preserved?
Some of the food is preserved for a couple of years, and then we say that it's expired, but expired means it's probably still safe. When we go to Mars, we need food to be preserved for 5 years, because we want to throw the food to Mars first and know that it's there before we land a human crew there. And it's a pretty big challenge to make food that's going to be good and healthy and hearty for 5 years. So, good question.
I think she's asking for the other girls.
Ah, okay.
You know it?
Have you ever tried CO2?
Have you ever tried CO2? Well, I produce 2.5 kilograms of CO2 every day, probably twice what you do. So carbon dioxide is a kind of a waste product. We breathe in oxygen, we breathe out carbon dioxide, and we have to have a system in space that scrubs that out of the atmosphere, because it's actually toxic, it's poisonous to us. So we create one of our worst poisons.
When are you going to plan to visit other galaxies?
Wow. So that's more your question than my question. We don't have a way to get to other galaxies. We don't even have a way to get to other stars yet. We need to find a way to get ships a lot further, a lot faster than we have right now. I give you that challenge. Go for it.
So there is currently an oxygen leak on the ISS, correct?
Not correct. However, what I'm sure you're referring to is there was an air leak. One of the Soyuz started to leak, and the atmosphere of the station started to go down, and they found it very quickly, and they plugged it with epoxy and stopped the leak. The story doesn't end there, but fortunately that Soyuz just landed, so that's not a problem. But what it tells you is that all of the modules and all the spaceships are open together. They share an atmosphere. So if any one of them leaks for any reason, the whole station starts to leak. So it's a big problem. So yes, there was a leak, and it was air. It wasn't oxygen, it was air. And fortunately, we found it quickly and we stopped it quickly.
Testing, 1, 2, 3, testing. Okay.
Testing back.
You guys said that 85% of the water you guys used is reused. If you guys, what happens to the other 15%? And if you guys keep not using the other 15%, or the other 15% isn't being reused, will you guys eventually run out of water?
Yeah, so it's a good question. We still have to launch some water to the station, new water. And we are fielding a new system which will actually get us at about 90% reclaiming the water, which is pretty good. But there comes a point when you're taking, so like pee, right? So you can only get down to about 10%, and the stuff is so concentrated that it's no longer practical to recycle, to get water out of it. And so this really concentrated brine, we throw that away as garbage. We'd like to get to 100%. 90% is pretty good.
Does it ever get claustrophobic if somebody has claustrophobia?
Yeah, it's a really good question. First of all, we kind of choose people who don't get claustrophobic. But a lot of people think that the station is claustrophobic. It's really big. And if you ever are feeling like you're in a small space, you look out the window and you see the Earth, and you get such an impression of bigness that you just don't feel claustrophobic anymore. You do in the little Soyuz, but not in the station. It's really quite amazing.
Do you ever miss like sports in outer space or?
You know, there are definitely, some of my crewmates will pipe up football games and soccer games and stuff like that. That's a big deal for a lot of the guys. When the World Cup happened, Germany, there was a German crew member up there, and so he was really happy about that. But in general, you don't miss that much from the ground, just because where you are is so magical, it kind of captures you. Like I said, we do have some sports-like things that we do up there once in a while when the camera's off, but yeah.
I have 2 questions. The first one is mine, the second one is his. My question is, what about the poop?
So, good question. We do not recycle the poop. We put it in a bag and we throw it away in a cargo vehicle that brings up fresh supplies, and we put trash in it and it burns up in the atmosphere. Today, eventually, we need to start recycling that also, or reusing it. So we will, and so we're working on that.
His question was, how'd you get the energy?
The energy for our bodies or the energy for the rockets or the power? You're talking about electrical power? Okay, good. So electrical power, we have solar panels, and when you're above the atmosphere, the sun is very strong. We have an acre of solar panels. It gives us about 80 kilowatts of power. So we're very fat with power, which is great.
How much radiation is in the space station?
So when we're above the atmosphere, we get a lot more radiation than you do on the ground. But because we're below those geomagnetic fields, we get less than you would in deep space. If anybody cares, it ends up being about 0.5 millisievert per day. The normal dose recommended dose for a person on the ground is 1 millisievert per year. That's the recommended maximum radiation dose. We get 1/2 of that every day. So we get actually a lot of radiation compared to people on the ground. But what we end up with is kind of a higher risk for cancer down the range. We don't get high enough to get radiation sickness. But it's a big worry for us.
If you're waiting for photos, please single file on the steps, guys, so we can keep them open.
Have you ever had any malfunctions on your rocket sometimes?
Oh, yeah. I mean, so the last time we tried to launch was about a week and a half ago. There was a malfunction as the rocket was launching, and actually between the first stage and the second stage, there was a problem, and the Soyuz, this was on the Soyuz, 2 of my friends were on there, and it separated, and they were able to land safely because the Russians build very good safety systems, rescue systems. But those happen, just because what you're doing is so dangerous. So once in a while.
I have to. How do you orbit the Earth without floating away?
You have to go just the right speed. When you're orbiting the Earth, you want to go exactly orbital velocity for your altitude, which for us is about 17,500. If you go even a little bit faster, you're in the wrong orbit, or if you go even faster, you leave orbit. If you go even slower, you start to come back to Earth. So the way you orbit the Earth without floating away is to go exactly the right speed.
And my second one is, if after being in space, doesn't it take 10 years off of your life?
No. No, it does not take 10 years off of your life. Boy. So far, we haven't seen anything that shows that astronauts live shorter lives. In fact, we tend to outlive the general public. And we worry about that because, again, the cancer risk, we soak up a lot of radiation. So we study every astronaut who flies from every country to see what their health is like over the long term and how long they live. And now, maybe we would live 10 years longer than even we do, but I don't think so. So, no, we tend to do fairly well health-wise.
Like you're older?
We act like, according to my wife, no. Not at all. Not at all. There's nothing, I mean, how old do you think I am?
59.
Okay.
You were born April 16.
Holy cow.
I just
Okay, yeah.
Googled you.
Yeah. Yeah, so I'm about to turn 60. I mean, we tend to outlive the general public considerably. When you look at the astronaut mortality, the ones that don't outlive the public are because they're doing something stupid. They're dying in aircraft accidents or mountain climbing, motorcycle. So, if we would quit doing dorky things, we'd even live longer. But in general, there's no effect on longevity from spaceflight for us.
I'm hoping to get to the person I told to be the back of the line, but we might have to cut it short.
I'll try to hurry you.
What's the worst part of it being in space?
The worst part about being in space? Being away from your family. No question about it. I mean, I have 5 children, and I missed a lot by being gone for 6 months.
How much did you grow in space?
How much did I vote? Oh, grow. I grew about an inch, 1.2 inches. And that's about middle of the road. There are some people who've grown as much as 2.5 inches. So the spine gets longer, so it's quite amazing.
What do you do most of the time in space?
Mostly you're doing science. Mostly you're doing everybody else's science experiment, many different ones a day. And then you're exercising 2.5 hours a day, and you're eating. If you take out exercise, science, and eating, then you're sleeping. You're busy. Every day is busy.
I have 2 questions. The first one is, did you experience any health problems after coming back from space?
After coming back, it takes a while to get used to weightlessness when you're coming from the ground going up there. It also takes a while to get used to gravity again. And everybody gets a little bit of motion sickness and problems with balance, and that loss of blood and fluid and everything that makes you really good for spaceflight, makes you pretty puny for the ground again. So it takes a while to get used to 1G again. And after your first flight, it's about 6 weeks before you're totally back to normal. So about that.
And my second question was, are plants efficient to bring into space?
Say again, I'm sorry, our plants?
Plants.
So we do a lot of research on plants in space because eventually we'd like to be able to grow food. We probably won't be able to do it on an orbiting station, but if we have real estate like on the moon or Mars, we might be able to. So we do a lot of research with plants, Arabidopsis and wheat and lettuce and various other things.
What happens if you put water in space?
If you put water in space? So if you let water go in the middle of the cabin, it will form a perfect sphere, a perfect ball, round of water. Anything, orange juice, use your imagination, any fluid will form a perfect sphere, and it will stay that way until it hits the surface, and then surface tension makes it spread out. So you have to we try not to do that.
I also have 2 questions. Why do they dehydrate food and then rehydrate it? Why can't you just use the normal?
It's a very good question. We dehydrate food because it can stay on the shelf a long time, and then we can add water whenever we want to use it. Our Russian colleagues are very good at flying canned food, which has the water in it. And they've developed processes where those cans can actually last a long, long time as well. But it's a little bit, it's difficult to do. So we use both, but it's all about water balance and food balance.
And also, is there another way you can communicate without using radio waves, like microwaves?
Possibly microwaves. One of the things that we're looking at now is laser communications, direct laser links, which can give us a really big, broad bandwidth. For low Earth orbit, that may be the best way for us.
I have 2. Do you have any plan to actually make your spacesuits better when going into space to help you avoid radiation?
Do we have a plan to help us avoid radiation? The main thing we want to do is to fly fast. So our biggest radiation risk is flying to Mars, which could take us a 6 to 8 month trip. Well, we'd like to do that in 2 months. If we can do that in 2 months, we save a lot of radiation exposure. So we need engines that will do that for us.
My second question is, if you know on the host fungi, macros or fungi, would you guys actually have plans to use that when growing plants in space?
It's a good question. The most efficient plant source for food is actually algae. Because you can grow a lot of mass really easily with algae. And so that's another experiment that we're doing. We're doing a lot of experiments on that, actually. Not nearly as appetizing.
On your first mission, how long did it take you to adapt to the zero gravity?
Boy, to get fully adapted, I would say about 6 weeks. We used to fly shuttle missions a week, 10 days, 2 weeks, and we said, yeah, after the first week, I really felt adapted. And then we started flying these guys on long duration missions and said, wow, I thought I was adapted after 2 weeks, but after a month, I feel so much better. And then 2 months in, they said, man, I feel so much better now after 2 months. I mean, it takes a while, especially your sense of balance, your position sense, and how to move things. So I would say 6 weeks for a first-time flyer. When you fly again, it happens much quicker.
Do you feel any effects of solar radiation while you're on this space station?
The only effect that you're aware of is what we call retinal flashes, where some of these charged particles will come in and hit a neuron in your retina, the back of your eye, and it'll cause a flash. And depending on the particle and the direction it's going and the energy level, you might see a yellow flash, a white flash, a blotch, a streak. Those are the only things that you see. And that's only when it's really dark and you're light adapted. But that kind of reminds you that you're in a radiation environment.
Have you built any suits to block radiation?
Of course, we have to use spacesuits to go outside, but unfortunately they don't shield you very much from radiation. They can help you with solar radiation to a certain extent, but the really heavy particles from deep space, they really don't help you that much. Which means that when you're doing the spacewalk, that's one of your most vulnerable times for radiation.
Do you get any free time in space?
You are allotted some free time. I remember not having a lot of free time. It's pretty scarce because you're always so busy. But most of your free time, you talk to your family if you can. And I don't feel like I needed more free time than I had.
2 questions. So the water recycler machine, approximately how big is it and how much does it cost to get it to space?
Oh boy. Well, how big is it is pretty easy. This poster here is about the height of a rack, maybe about 10 inches taller than a rack, about very close. And if you had about 3 of these, that's how wide those 2 racks would be together. And then it's about half of that distance back that way. So it's big, it's a lot of machinery. How much it costs? I have no idea. A lot.
And my next question is, approximately how many times can you recycle the same water before it gets bad?
Well, you can keep recycling it forever. You just know that you're going to lose about 10% of it for each cycle. But the same water molecule can come around many times, just like on the Earth. You know, there's a water cycle. It rains, waters plants, the plants are eaten by us, we eat them, we feed, it goes into the ground, down the river, and on again. So those water molecules come around all the time.
What stupid games do you play?
Yeah. So one of the things that okay, I'll tell you just a couple of them. I mean, I like to fly fast and
Please tell me all of them.
well, I can't say all, I don't have time, but if you've got a bunch of modules with small hatches between them, one of the cool things to do is to push off from one end of the station and try to thread the needle, fly through all of those hatches without touching anything. That's hard. It is really hard. Another thing we might do, not saying we do, but we'll take bungee cords and string them against across a hatch, and you can take a big bag and use it as a slingshot and see if you can just get right through the hatch. If you don't do anything that might hit something and hurt it. But it's really very interesting because when you throw something or when you launch yourself to jump on the ground, you're always putting an arc on yourself because gravity is always pulling you down. So if people shoot a basket, they shoot in an arc, and somebody throws you something, they could throw it in an arc. Up there, it has no meaning. So you throw everything exactly straight, and to untrain yourself and putting that arc in there is really quite formidable. So that's one of the reasons we do those games. It actually helps us. Yeah.
So, I have 2 questions. And the one is, when you land...
Here, now the head coach with the Giants, obviously his hands are full.
Touchdown. I mean, home run.
What do you mainly need to recover?
What do you need to recover? So you land weak, and you land anemic, meaning low blood cells, and you land dehydrated, low blood volume. So what you need is to replenish your blood volume, replenish your red blood cells, and get your strength back. So we have these really sadistic strength and conditioning coaches, basically sports trainers that know how to rehab people from space, and they start working you. It's like going to boot camp as soon as you land. You start an exercise program and a rehabilitation program, and you do that every day until after about 6 weeks, you're pretty much as strong as you were before you left.
On those food things you showed on the picture, don't the food inside just float away?
Well, so the food that I showed you on the picture was all down on the table, and it was held in place by Velcro and tape. So it was actually stuck down so it wouldn't float away. And we choose sticky foods that don't, bread that doesn't crumble and stuff that doesn't come out of the cans.
The last one.
Oh, sorry, guys.
Is it like scary landing and going up?
Yeah, like I said, if somebody asks me, I was nervous. If you're not a little bit scared, you don't know where you are. But mostly we're very focused on the job that we're going to do. And so, again, I would say that it's still scarier for our families than it is for us. But there's tremendous energies that are going on there, so you just have to be mindful.
Okay, we have to bring the next group in 8 minutes, but we're going to try to get this line down here. So please, in orderly, one team at a time, please bring your whole team down at a time. We do have posters if you're looking for something to be signed.
Can we bring up the outfits?
I want to go, sir. Shot Lou. We need to go on the Shot Lou.
Get up here, Josh.
Well, you can, it's very easy to use martial arts. You're using your tongue to way. It's all about So that's what we worry about. Oh my.